There it
Here
is.
we are.
Okay, we're on. Thank you very much, Tom.
I'm 5 minutes late, which means we'll
Hey.
go five over at the noon hour. And doggone everybody, happy holidays. We're trying to. Happy Turkey Tariff Day, everybody, this week from our astrophysics house to yours. And welcome to the SBAU Astro Hour, number 248. And wrapping up our 5th year of broadcasting, I guess that could be the term. I'm Ronnie Herron, your host, on behalf of Santa Barbara, California's longtime telescope club. And it's based at our town's Museum of Natural History, the Santa Barbara Astronomical Unit, which is good old SBAU. We're going to meet our other great members of the club in just a minute here, but here's a rundown of cosmic topics we're going to take on. A little late, we're sorry. Thank you for hanging in there with us. And this is for the coming week here, starting today, November 24th through the 30th. We wrap up November 2025. We got a recent photo of our interstellar comet visitor, 3I Atlas, up to the Andromeda Galaxy to catch a couple of galaxies. And there's one called the Silver Sliver. Wow, news to me. And
Yeah,
tomorrow,
say that fast 3 times.
Yeah, I was going to say, yeah.
I've never heard of it, gentlemen. We all got to learn something first time, every time. By tomorrow, our moon is a nearly 6-day-old crescent, and we're going to check out some craters and mares on its surface again. What in the world do the letters B and H have to do with the sun's magnetic field? Are they sunspots? Well, it's an apparent hole in our sun's corona. We're going to find out. Existing theories, ladies and gentlemen, about the solar system are being challenged with a newly discovered TNO, that's trans-Neptunian object located out beyond our 8th planet, called 2023 KQ14. It's an all-new sednoid called ammonite. I have a sednoid problem I have for years. Terrible allergy. Let's
I have a deviated sednoid.
That's right. All right, gentlemen, we're still slaves to modern technology as it keeps being taken over by AI. We're a little late today. Here's our beloved president after 8 years, Jerry Wilson, up for re-election again. Jerry.
Morning, everybody, and good morning to Riley and Calvin, who might be watching this together in Oregon. I hope so. Hello, boys. And to my sister, Joyce.
Oh, she's the one lady that sometimes you do 2 ladies, don't you?
No.
Okay. Well, he's married to a nice lady. Very supportive.
Except for Mrs. Calabash, wherever you are.
Right.
You and Jimmy Durante, huh?
Like Mrs. Miller used to go to all the talk shows and watch in the front row. Pat Forgy is his wife. And our Santa Barbara Astronomical Unit outreach coordinator is the unflappable Chuck McPartland.
Hello.
He is. He's also married to Pat McPartland, who is merchandise manager and an incredible treasurer, running again in the next month, which is a couple weeks away. We have our elections. We have on screen, I'll take them chronologically as they joined us, Bruce Murdoch, who's married to Bonnie. Bruce.
Hello.
Right. Good to see a little slimmer version of him because he joins us, I think, by way of his iPhone, right? And he is president.
Right, I'm on my iPhone. No, not iPhone, it's an Android.
Well, we got rid of that terrible backtalk, double speak, whatever feedback, I guess we had for a while there. Speaking of problems, Bonnie is his wife, and the Theater Organ Society is his other love since he's president. Tim Crawford joined us, resident lens expert. How are you, Tim?
Pretty good.
So hard to get him to open up and talk to us, but doggone it. I'm going to tell everybody some year in December, he's going to do an incredible presentation at our members only in-house.
That's right. I'll light it up.
That's true. And he's married to the lovely wife, Karen. And doggone of Tom Whittemore, our long time, I discover, newsletter editor. How are you, Tom?
Fine. Thank you.
Married to Maureen, and he's also a bird watcher and a nightly telescope watcher. And he's just a great guy, retired happily and joining us on screen. And how many years do you know? I think it's before Jerry was president. You were still editing our newsletter.
I think it goes 21 years. Chuck will know. But
wow. Yeah, it's back to the early 2000s, definitely.
Yeah.
So for a long time, we had 2 local professors from colleges. Sean Kelly, Santa Barbara City College, and you from Westmont. Yeah. Okay. Well, here's how the president of the club sent it to us on our inboxes this week. Tunes for the 24th. We like to start the hour with our silly science cartoons that are forwarded by Jerry, and there's 7 or 8, a couple of which I'm going to need explanation. Could be one of them. Yes, troubling news. The girl, is this a new generation? Whatever, what are they called nowadays? Z or X?
Alpha. The new
Okay.
generation's alpha.
Why don't you read it and explain it, Mr. President?
Oh, there's a troubling new survey that shows that 90% of graduating high school seniors don't even know the airspeed velocity of an unladen swallow. Now
Swallow as in bird or swallow as in bird?
Yeah, it's a bird.
Yeah.
It's a reference to a line, what is it, a puzzle? A puzzle in Monty Python's movie, The Holy Grail.
Really? They do this line?
His group came up to a bridge and the wizard was standing there and he said, you have to answer my question correctly if you want to cross the bridge. And someone takes a guess at it and they're wrong and they get thrown away. And then the next guy steps up and he said, and then he gets this same question. And he said, is that a European swallow or a North African swallow? And the wizard goes, well, I don't know. And he gets blown away. And the group goes across. So it's good to know these little trivial facts.
The only thing I remember about Holy Grail movie was arms being cut off and blood spurting. And Monty Python, they were weird.
Yeah, that was just a scratch.
I know. We were all Python freaks, weren't we? All right, do another one here. Now this was not sent to us.
No, this was new this morning.
All right, who's talking there and what are they saying? Anybody want to grab that?
Dad, we must find some means of discarding this hideous thing. I
Oh,
think
it's
this
a
is a repeat
boomerang?
years ago. Yeah.
Oh, boomerang.
Oh, they got bumps all
He's
over
got a
their
lump on his head.
This one I know we did, but I couldn't resist.
Yeah.
This is
This
a
one
gate
you know
of
you didn't
gates.
get. So you're going to have to explain it. All gates in one gate? What does that mean?
I'll bet you Bruce.
They're logic gates.
Those are logic gates.
Yeah.
That's
See, every
what
one of these symbols is a circuit logic gate.
Oh, no kidding. And
So
what?
this is a gate made out of electronic gates.
And that would be in the discipline of what? Physics or mathematics?
Electronics.
Electronics.
Boolean algebra.
Okay. Haven't yet seen those. Okay, now this one definitely needs some explanation. 252 has some meaning and
But it refers to this page.
it's what?
It refers right back to this same page.
Okay.
This is a Unix manual.
Okay. They're listing the contents on page 252 of this ledger or whatever. Is that what you're saying?
This is an index,
Right,
Ronnie, and it's telling you where to find the definition of or the mention of infinite loop, and it refers right back to the same page.
We just keep
So
going.
it's a meta definition. It's referring to itself.
It's a joke on computer programming.
Yeah.
Put it in there. Okay, I think I can buy that. All right. The moon does affect our pools, does it not? Anybody want to read this? Tom Whittemore, how about you?
I told you this house was too close to the moon.
Quick, Margaret, grab the surfboard. Is this Gregor Mendel?
Yeah.
He was he wasn't a priest, was he? He was a Protestant, I think, right? Or was he
he was a
Catholic?
Oh, he's a monk. He was a monk.
So he's Catholic. And he, I guess, played with the genetics of peas,
Yes.
dominance, and recessive genes. And guess what all the fellow monks and brothers had to eat every night? So who wants to read that one? Chuck?
Brother Mendel, we grow tired of peas.
Yes, we do.
I don't get it.
Well, he was growing peas, Tim.
For
Oh,
genetic
You said
studies. Tim.
genetics.
Oh, okay. I didn't know that. Okay.
He bred peas.
Mendel did peas. What did he come up with a conclusion? Anybody know?
Genetically modified food. No.
Yeah.
Is that what it was?
Yeah.
No, he came up with the idea, just as someone said earlier, of recessive and dominant genes and how one would express over the other and how they're transmitted.
Mhm.
But
He
he
didn't
had
know the mechanism, but he saw the effects.
Right.
All right, we have Six views of a physicist, how people consider him. Anybody want to take this one on, Mr. President?
What my friends think I do.
Yeah, Einstein at the blackboard.
What
Okay.
my mother thinks I do.
Just one thing, nothing, and he scratches off his to-do list every day.
What society thinks I do.
That's got to be Frankenstein and Terry Garr, right?
No, this is Back to the Future.
Oh,
That's
that-
Mad scientist.
It's a really good
Gotcha.
movie. Great
What
movie.
mathematicians think I do.
That thing. Killed him.
We used to have a joke in physics that if you couldn't solve an equation, someone would say, well, go ask a mathematician. And they would, the idea was that they would tell you everything you wanted to know about the equation, except how to solve it. And here's what I think I do.
Yeah,
That's right. Nikola Tesla doing miracles with
yeah, it's
electricity.
Tesla. Mhm.
Yeah,
And what I really do.
that's right. Nothing
Yeah.
but
And this is
Forums,
quantum mechanics.
formulas and-
It's quantum mechanics.
okay, and equations. Okay. Oh, here's speaking of playing with genetics or whatever they're doing here. Vegan scientists mixing 27 carcinogenic chemicals in an attempt to make a soybean taste like a hamburger. Somebody's going to tell the vegans they don't care. And here is one of the first problems ever involved with mankind.
Well, they don't live that long.
What doesn't live that long? What are we talking about there? It was a beautiful day for the sun was
The
out
people that
shining.
they get the genetically modified foods to taste like a hamburger.
Since you're talking with us here, Bruce, why don't you dissect this cartoon? Read the caption and tell us what we're looking at here. Or did you get him?
I'll do it.
You're breaking up.
It was a beautiful day. The sun was shining. And Zog had just finished washing his new invention.
The wheel, and it got
This guy
dropped
had
on
just
by a pterodactyl, dropped a little dropping, a little gift. God knows we all have those, don't we? All right. That gets us in a stupid, silly mood, kind of like Tuesday night workshop. I'm going to try to join you guys tomorrow night if I can find my link to who's on there. I guess Tim's not joining us. He's got Thanksgiving duties, right?
Ever since we've signed in, now I can't chat on the YouTube side. So
Maybe he doesn't have the password.
I don't know what's going on, to be honest with you.
Sorry,
You're not
folks.
You're not getting the comments at the bottom of the screen.
I'm not getting that, no. So I gotta play with it a bit, I think.
What happened to our young man? I assume he was a young man over in India. Used to watch us in the middle of the night, the Indian subcontinent. Okay, where are we here? This is our visitor.
This is a picture of one of the few credible pictures. You can see pictures all over the internet of wild science fiction-y claims from this thing. But this is from October, what was it, 2nd? The high-rise camera on Mars. Image captured by the space science camera. Okay. Of 3I Atlas, you can see this is the direction the comet is going in. It put a nominal guess at diameter at 932 miles here. This is the coma, and this is the nucleus. It's always hard to tell the size of the nucleus from pictures like this, but it's the best they can do. That would be nearly 1,000 miles across. That's a big.
Yeah, but that's not the nucleus, though. That's just the
No.
brightest part of the coma.
That's correct. So you
Does
know,
anybody know how this is traveling in relation to the plane of the orbits of the planets?
no, I don't recall.
It's roughly in the plane of the ecliptic.
Is that right? Did it go by Mars recently?
Yes, that's why you got this high-rise picture from the Mars Reconnaissance Orbiter.
Yeah.
Oh, okay. Well, then that's where I read it or heard it. Okay.
So these things you see with flames dancing behind it and all sorts of things, which I've seen lately, even K1 Atlas claimed to be 3I Atlas. It's not.
Yeah.
So, and that's so famous. I don't know whether they're doing it by accident or purpose, but this is what there is.
Actually, there's some much better pictures taken from Earth-based telescopes, especially those guys in South Africa.
Yeah.
that show a really nice tail, the green glow from diatomic carbon, the whole thing. It looks like a classical comet.
Oh, I haven't seen those.
Spaceweather.com.
What's that?
Spaceweather.com.
Can you call one up while we're doing this?
Okay, I'll go ahead and continue while I try to get a good one.
Okay.
Well, if it has a long tail, is it facing away from the sun? Normally,
Always.
Yes.
always.
The ion tail faces away from the sun.
Yeah.
I think I got YouTube working again, so I'm set.
All right. So this is the night sky around 10 o'clock these evenings. And you can see the constellation of Andromeda up here. And we're looking at the galaxy in Andromeda, but not the big one, not M31 or M32 or M110. We're looking at NGC 891, also called Caldwell C23.
Oh, okay. I didn't get that. Okay, I got it now.
Okay.
Yeah.
So
So
this is over, you just go to Almach, and it's 3.5 degrees from Almach. So it's an easy object to find, and it's a very dramatic picture. It also is one of the pictures, if you remember the Outer Limits TV show from the 60s, they sign off with the credits after each hour-long episode, and they show a series of astrophotos taken by the big telescopes of the day, mostly Mount Palomar's 200-inch. And one of them is this galaxy, the Silver Sliver, it's called. Say that fast 3 times. And this is what it looks like.
Yeah, it's pretty bright, Jerry. You've probably seen it, huh?
It's what?
It's extremely bright. You've probably seen it, right?
But you're not talking about the picture, as you
No,
can see.
891 is real. It's a real bright galaxy. It's pretty easy
Yeah.
to pick off.
Yes.
Mhm.
See it naked eye?
No,
I wouldn't say
it
that.
could possibly in the dark sky be seen by binoculars, but it's I've seen it in an 8-inch.
So this is magnitude 9.9.
Mm-hmm.
So you would stand no
Okay.
chance of seeing it.
Yeah.
So you'll need a scope of at least 10 inches or larger to see this in
think-
the dark sky.
Tom Totten sent a text to me. I think it's referring to the comet though, where he said you go to skylive.com
Well, here's
slash.
here's the image from Space Weather. Is it okay if I share it?
Just a minute.
Okay.
Okay.
Image of this sliver we're looking at.
No,
It's of a
the
comet.
image of Comet 3I Atlas.
Oh, we're going back to that. Okay.
Yeah, and I think that's what Tom was trying to send a link to see the image.
Yeah. I can't share right now because of 891, the silver sliver there.
Yeah, you have
It's already
to
being
stop
shared,
sharing,
yeah.
Jerry.
I've got a freeze up computer here.
Uh-oh. We got a little everything today.
Yeah.
Yeah. Well, we're going to continue on with this. No, we're not. We're going to get rid of this. Okay, I might have to get off and get on again.
Ouch.
Oh dear.
Uh-oh.
That leaves us floundering out here in the water without captain.
It's probably easy to get off, but you're not gonna. Maybe you won't be able to get back on again.
Oh, we got passwords and all that.
A couple of AU folks went up on East Camino Cielo last night, and Brian got a good picture of this 891
Huh.
with his sea star.
Mm-hmm.
Yeah, that's what that was. Okay.
Yeah. Looks a lot like the needle, Tim.
Yeah, it does look like the needle.
They went up to our favorite spot on East Camino Cielo.
Not that one. It's a different one. Kind of the
Oh.
junction at Painted Cave and East Camino Cielo.
Hmm.
Well, that's a lot lower. There's a big field, a big flat area there. Yeah.
Well, are we frozen in space, gentlemen?
No, we're okay now.
Oh,
I
we
think-
are all right.
Yeah, I
Can
think
you-
All right.
think-
Okay. So I'm going to share.
Okay.
I think so. Yep,
Wow.
you got it.
Oh, that's very nice.
Oh wow, that's a good picture.
Yeah.
That's our Atlas visitor.
Yeah.
This was taken by a large telescope in South Africa, is that correct?
It's not a particularly large telescope. It's a 12-inch telescope.
Oh, wow.
Yeah.
And you sure this is 3I Atlas?
Yes.
Okay.
Now, I think Tom Totten was saying you can go you folks out there can go to the skylive.com /C2025N1 dash info and go to the bottom to 3D orbit view that one you can tilt it around.
Well, that will show you the relative to the ecliptic. Yeah.
I think
Yeah.
so. Anyway, that he was sharing that with everybody.
Okay.
Wasn't he on the screen with us once?
Who?
Yeah.
He could have shared that live right now with his ugly face up there like ours.
Come on, Tom, you heard him. Get up there.
Were the two predecessors to this atlas, the Oumuamua and the Borisov, were they also comets?
Yes.
Yeah.
I don't recall ever seeing a picture of a tail off of Oumuamua.
No, I don't recall one either.
No, it had a different composition. It seemed to be more hydrogen ice, and so it didn't have a visible tail.
Yeah.
Okay, but that the tails are required, or the water is required, right? Ice.
No.
No.
Sometimes CO2 becomes a tail,
Yeah.
or all kinds of other materials. All right, let's go to the moon. This is
It was an asteroid that we landed on, or we were near, and someone noticed the star patterns were changing behind it, and then they realized that it was pebbles emitted from the asteroid. So in my mind, I thought, well, that was an asteroid that was re-promoted to comethood.
That was Bennu.
Bennu, that's it. Okay, this is the moon Tuesday evening. Can you see that okay?
Yeah.
Okay. So this is the percent of crescent we have. And up in this region, there's an interesting crater, very interesting crater.
We're going to get close up to right now.
Yeah. The crater is Berg, and it's a big crater with a central peak, and it's smacked right into the middle of this, what's now Lacus Mortis, which means the lake of death. Should say, where something big hit and broke through the surface, and it filled up with lava and froze over. And then later Berg came along.
Berg. As in iceberg?
It's a Rockberg.
Rockberg.
Or
Pittsburgh. That's where, Pittsburgh is
Regulus.
Got it.
Okay. Now, I promised Tim we'd discuss a little about magnetic fields in the sun. So don't be scared by these formulas. They're very easy that I picked out. We're not going to do any calculus.
I got confused.
Okay. So this represents a wire, and there is current flowing in the wire. Now you remember, because science discovered, they knew something was flowing in wires, and so they labeled it electric current, and they arbitrarily assigned it to the flow of positive charges. It turns out
Benjamin Franklin.
right, the thing actually flows the other way. It's actually electrons flowing against the arrow. But when you see an arrow and an eye for current, this is the flow of the current, but the flow of electrons, the part that's actually moving, is going this way. Now, when you, but that's a little annoying thing in the background.
Yeah.
And also you can tell these books and discussions, whether they're made by an engineer or by a scientist. The scientist will use lowercase I or lowercase j for current density, and use lowercase I for the square root of -1. Engineering text use lowercase I for the flow current density and lowercase j for the square root of -1. So, but that's not here nor there. That's just a little side effect. So the current is going this way. And if you put your thumb in the direction of the current, then your fingers will curl around the way the magnetic.
Your right hand.
The way
Got to be your right hand. Yeah.
Right hand, Tim.
Right. But if you want to know from the left, if you want to do the electrons flow this way, and you still get, and you get the wrong way. So you get, you have to do it the right way. This is where current goes. And the magnetic field goes around this way. It's a circular field around this. Now, you do not have to have the magnetic field is called B, capital B, because it's a vector field. And it's given by, at the point R from the wire, it's given by this formula. This is the permeability of free space, in this case, which is 1. This is the current, which is a vector. This is a vector, and this is the radius, the distance you are.
So permeability of free space is 4 pi times 10 to the minus 7th.
That's right.
Okay, so this
Not 1.
We're going to ignore it for right now.
Okay.
That worked for me.
Okay.
The units
We're
are
going to do
Henry's per
everything
meter.
in units of mu0.
Yeah.
Yeah. It's okay. I'm oversimplifying here, I know, but the gist of the physics is there. So the point is that you do not need to have a crowd of electrons going this way to be a current. You don't need the wire. You can have a single electron flowing this way to be a very small current going this way. And as it goes by, it produces this B field. Now, if you are standing here and the electron goes by this way, you will see this B field as long as the electron is passing through this region. If there's an electron sitting here and you are passing by going this way, the person moving, will feel the B field, but there won't be anyone standing here statically with respect to the E field will not feed a B field, will not feel the magnetic field. So a magnetic field is produced by a moving electric field, or a moving source of an electric field, a moving charged particle.
It's got to be the electron. It's never the proton.
It could be a proton.
A proton will work too. We're getting to that.
Anything with a charge.
That's correct. Anything with a charge. It can be a proton going this way. But in a wire, the solids are made out of a lattice with all the nuclei bonded to each other in some kind of a bond. A covalent bond, an ionic bond, a hydrogen bond, a cool something. And so they're not moving. It's only the electrons that move in a wire. If you have free space and you can move a charge, it doesn't matter. It could be protons, and in our case, in the sun, we have atomic nuclei which are positively charged, and we have electrons which are negatively charged. So we get magnetic fields going in all these different directions. Now, when a magnetic field is there, so you see the charge produces a magnetic field. This is Lorentz force on a charge. This charge is Q, which is, for example, a single electron. And this is its interaction with the local electric field, plus the velocity times cross product of the B field. So this, again, is a right-hand rule. And so this is, not only does a charge make a magnetic field, the charge reacts to a magnetic field. So the magnetic field actually tells the electron where it's going to go. So this can get quite complicated. On the sun, you have a fluid made out of plasma, which is atomic nuclei and electrons, and they're moving in all sorts of crazy ways. Turbulence flows in response to electric fields from the charged particles and magnetic fields from the moving charged particles. That would be, to figure that out, that would be a field thing called magnetohydrodynamics. And you have to be in love with math.
Yeah.
Yeah. Now, this is a very nice. What's that?
It's the fourth state of matter.
Plasma. Yeah. I've heard that they're trying to claim that a fifth state of matter is a time crystal.
Whoa.
We'll see how far that gets.
That's what we need.
So anyway, this is a magnetic or a evacuated sphere with a slight amount of gas in it, so that when electrons hit the gas, they emit light. Now, and this is an electron gun. You have a fiber down here that is hot, so it's emitting electrons, and you have a couple of plates here that accelerate the electrons from the cloud back here out through this hole. And then once they're out of this region, they're passing through a magnetic field that is a straight line here. And this is the Lorentz force moving the electrons in a curved path. That this operation here, which is the cross product, gives a result, a force that is at right angles to the B field and to the velocity.
This is the Lorentz force here?
This is the
Yeah.
Lorentz force.
Okay.
And this is the Lorentz force moving a particle, an electron of mass m sub e, in an arc. This is the response of an electron beam to a simple straight magnetic field. Now this
There's
is
a wire.
what's that?
There's a wire between those two poles. There's a wire between those two poles that's carrying current.
Which wire are you pointing out?
You have the two things that are called like telephone poles with cross arms on them.
This thing's
Right.
This I think is an electrostatic. There's a voltage applied between here and here, and then there's current that is supplied back here where it glows. So this
Mhm.
thing, when it glows, it's emitting a cloud of electrons, and then they're getting sucked up by a electric field and accelerated this way. And then once out here, they're in a B field, and so that goes that way.
Exactly. That's why it's circular.
Yeah, I don't know what these are due. They look like they're connected metallically here, so they're just structural supports, I would guess. But the B field is applied from outside. It goes through the glass ball globe.
Oh, okay.
And this is also used as a mass spectrometer, because if you have something else, and these are used on the Mars rovers to identify materials. So if you accelerate these, in this case, electrons, but if you have something else like atomic nuclei, which is a different mass, or a proton, which is a different mass, they will come out and go their own way. A proton would go this way, but a negative charged nuclei would go out this way, and it would land somewhere else. So
And depending on the different masses, they'd land in different places. So
Right.
that's how you can tell what's there.
that's right.
It's
Right.
your mass spectrometer.
Yeah, one of the ways of identifying species of what you're throwing around in there. But positive charge things would go this way.
Ron, any
You
guess?
got it,
at-
Ronnie?
Ron, any
Now,
guess
what
at the gas? What gas would you think is in there?
Yeah,
Probably helium.
no,
Well, the caption said oxygen.
Oh, did it say oxygen? Okay.
But you
That's
can
the wrong
put,
color for oxygen.
this is also,
I've always heard that current goes at the speed of light. It doesn't, does it? Because
No.
electrons are technically matter. Matter can't go the speed of light. So how,
Right. They
How
have
fast-
that.
particles
You know-
move at their drift velocity, which is equivalent to a terminal velocity for something falling through the air.
It might be nitrogen that's glowing there because it says air, not oxygen. My
Right.
mistake.
I would have guessed nitrogen, just the color.
Nitrogen glows in the orange.
Depends on the electron, on the ionization state, though.
Right.
Okay.
Okay. Now,
wow. Yeah, put
So-
those wires in a coil and you double it up, don't you? You increase it.
so here we have a magnetic field line, and here we have an electron that does not smash into some plate to measure where mass it has. When it shoots along this way, it just spirals around the magnetic field line. So here's FQ V cross V, and there's no E field here.
Mhm.
We're just looking at the magnetic component, but the QE, the electric field force, is there too. But what happens when this goes around? An accelerating charged particle emits a kind of radiation called synchrotron radiation. And it does not have the characteristic line emissions of an atom where you're jumping from energy level to energy level. And this is the primary source of radiation from the sun, from the surface of the sun below the atmosphere, which is gives it that uniform black body radiation. There's no emission lines in it because there's no atoms in the sun. There's just some kind of charged particle zipping around and producing synchrotron radiation. And so the magnetic field, the charge moving makes the magnetic field, and it also reacts to the magnetic field. So, and now this is a little poor picture, but I didn't want to redo it. It wasn't worth the time.
But there's no electrons, you're saying.
No, this spiral is an electron. See, it says electron path.
Right, but a plasma is so hot that the atoms are dissociated. They no longer have electrons spinning around protons. They're just a soup.
Right. As Bruce points out, the electrons are not captured by a nucleus. The electrons, the nuclei are completely ionized. Besides, it's mostly hydrogen. It's just protons and electrons.
Okay.
You're going to, through fusion in the core, you're going to develop heavier elements, and these will be up here too, but they're not the dominant species. I think the sun is 75% hydrogen still.
Okay.
So this is a discussion of magnetic flux. This is a magnet up here, North Pole, South Pole, and the complementary one down here, North Pole, South Pole. Magnetic flux lines do not start and end here. This flux line goes up here, goes through there, and it's the same flux line out there. But where their flux lines are denser, where they're closer together, the magnetic field is stronger. So here, this is more flux, and this is less flux. So when it's spread out, it's not as strong an interaction with particles.
No, Jerry, when you refer to it as flux, you're not talking like a soldering iron with
no,
flux.
that's a different. No, that's analogous to the word plasma for blood products.
Okay, so this is more of a flux, is kind of a bending of.
It's a concentration. See, these are closer together.
Okay.
The flux is defined as the number of magnetic field lines that go through a given surface. So here, if I draw a circle, there's more that goes through there. And if I draw the same circle out here, there's fewer that go through there. So the magnetic field is weaker out here than it is here. Now, when you look at magnetic field lines and flow lines for magnets, you're tempted to think that it's the same somehow as iso altitude lines on a topographic map. They're not. It's not related.
Huh.
Now the complementary north and the blue and red on the bottom, why isn't that upside down there?
I don't understand.
So in other words, that they're both have north side up on these.
Yeah, north,
Yes.
south attract. So lines
okay.
through here and up there. If I were to flip this one over so it's south above, then you'd see the lines flare out and never go to the other one.
And they repel. Okay, got it.
And Tim, the convention,
Yeah.
the convention, Tim, is to go from north to south.
Yeah.
Okay, from north to south.
Mhm.
Okay, now
You see how the
also,
lines go, Tim?
when I'm discussing on Sundays about the different sunspots,
Mhm.
when these weak lines come and the plasma pops through, they're going to travel from north to south.
Yes, but you can't see which way they're going on this.
Okay, but that's
But this strong field is where you would get a sunspot.
Yeah.
This is the portion of the sun away from the sunspot because it's a weaker field.
okay, good deal.
So,
Mr. President, did I misread your talking points? You said there were two letters, B and H.
yes, yeah. I started out with grand plans, but I didn't. After I got going, I thought putting the H in would be a complication.
Yeah.
But
okay.
if I go back here,
B equals mu H, where mu is the permeability of free space.
yeah. So the difference between B and H is a mu. So it's just where the mu is located. If you have free space, then this one is for free permeability of free space. But if you have a material, then the material has a certain permeability. And I got to thinking, what's the permeability? And I got to thinking, what's the permeability of a plasma in the sun? But I didn't want to pursue that for this.
It's complicated enough for me, I'll tell you.
I'm simplifying.
There'll be a test. There'll be a test.
Do those letters stand for a word? Is there a B word and an H word that starts with those letters?
B field and H field.
Oh, field.
H is the magnetic intensity and B is the magnetic
field.
flux.
Okay.
Yeah.
Field.
Okay, now this is very this is an illustration of an Alfvén wave from a black hole. And what happens is that these this is the emission line or emission cone from a black hole, the disk around it, and it is bundled up with electrons producing magnetic fields and electrons reacting to their own magnetic field. They're all clustered together, and you can generate an energy wave that moves down this cone of stuff. And this is the wave moving down there. So it's a good example of an Alfvén waves. These occur in the sun. They occur as they're leaving the sun with CMEs. This was such a nice diagram, but this was a diagram from a computer model of a black hole jet. But you get, this illustrates the fact that once the magnetic field is going, it's captive by the charge, and the charge is captive by it. They have to work cooperatively with these two laws, generating the field. And it's very complicated in the sun because you've got gravity as a force in there too. And you've got, as Bruce pointed out, you've got all this heat motion, this random energy buzzing around. So it's a nightmare in there. To think of the sun as just a ball of fire is missing most of the important physics of the sun. A friend of mine wrote a PhD thesis that described propagation of sound as one of the chief mechanisms of energy going, not particles, but energy going from the core of the sun to the surface. So you have that's part of the heat source too. So,
but what you were showing there, it comes out of black holes. Did I hear you say that?
This is a jet that you sometimes see, for example, out of M87, the black hole at the core of that. You see one of these relativistic cores coming out, or jets sticking out of M87.
Oh, I see. So it's not Hawking radiation, or
no, it's not Hawking radiation.
And it's not the
Hawking radiation is a dull glow around a black hole.
Got it.
This is
the way black holes evaporate.
What's that?
Yeah.
Oh, yes, the Hawking radiation.
Okay.
Okay, now this is
the Hawking radiation evaporate. Yeah.
Okay. Got it.
Takes a long time though.
Yeah.
This is a composition of from September 10 this year, showing a coronal hole in the sun. Now these are only visible in UV, so or soft X-rays.
Yeah, that would be a soft X-ray 195.
Yeah.
So some people called it extreme ultraviolet, but at Lockheed we called it soft X-ray.
Yeah, that's
we
right.
171, Jerry.
What's that?
We worked at 171 angstroms.
Okay, instead of 195.
A little hotter, a little hotter.
So Tom used to work in solar physics.
Yeah.
So this is a weak spot in the sun's corona, where the magnetic flux here is fairly low, or excuse me, it's fairly high, because your is that right? Do I have that backwards? Anyway, I'm not an expert on the coronal holes, but this is a danger zone for CMEs coming out and heading for the Earth.
And for just the solar wind in general, coming straight out.
Yeah, I think I saw that on a program where they were talking about the emission of how everything accelerates out of the sun.
Yeah,
is due to these coronal holes.
Now this is the Wikipedia, and one other source said that this is where open electromagnetic force or open magnetic force lines just drive particles straight out of the sun here. And that's why it looks cooler. It's like where the flux is high, it's like a giant sunspot, but that doesn't make any sense the way they stated it, because magnetic field lines are always closed loop. There's no magnetic field lines that come straight out of the sun. But an electromagnetic force in using Lorentz force, there is an electric field that can come straight out of the sun. Yep. And so I think that's what they're referring to. Anyway, this is we're looking right down the bore of this rifle for the sun.
Right. And Ron, it's taken from a GOES satellite, because all this stuff would be eaten up by our atmosphere. We couldn't get this image. So
but it was that big. It's shaped like a butterfly, and it's
Yeah,
bigger
it does.
than a
Looks like
sunspot.
butterfly effect, huh?
Yeah.
Yeah, yeah.
They take all, I picked this one because it looked like a butterfly. They come in
That's
all
really,
sorts of shapes.
really, really intense. It's really beautiful.
So it's a totally different thing than a sunspot.
No, it's similar.
It's
Oh, it is similar.
It's dark here because it's cooler.
cooler.
When you have heat is simply the motion of particles. When you have things that are hot, they're all wiggling and moving all over the place. When you punch a magnetic field line through it, they don't have the freedom to completely respond to all the collisions with all their neighbors. Now they're confined to move along the magnetic field lines. So that takes away a little bit of the randomness, and they cool off because of that. They appear cooler.
Yeah. I was just going to say to Ron, to give you a feeling how hot this is. Again, I worked at 171 angstroms. At that temperature, iron would be ionized about 17 times. So, the element that contains 26 electrons, okay, 17 of them are gone.
That's
It's
also
got
the
only,
element.
it's got only 9 left, and it's positive.
Yeah, it's pretty hot.
Isn't that
So
also,
in our solar scopes, a coronal hole, it won't appear white, brighter. It would actually look darker, like a large sunspot.
No, you
You
can't
won't
see it.
see it.
Can't. This is in far UV.
Right. Tim,
Okay.
remember,
okay.
you're looking at a red line of hydrogen. Okay.
Okay.
This is hotter than a cootie bird.
Okay.
but does this affect our auroras on Earth?
Yes.
Sure.
Oh, gosh, yes. Yeah.
That's why we're seeing them really low
Yes.
latitudes.
Yeah, and
Those-
Ron, I was thinking about the auroras when Jerry was showing those previous images of these electrons coiling about magnetic fields lines. And so some of these electrons coming into Earth from a solar burp, there you go. So imagine that electron or a proton, those are things that come to the Earth in the upper atmosphere from the sun. Imagine that thing just whacking into nitrogen and oxygen and all kinds of neat stuff in the upper atmosphere. Okay, so they will circulate about our magnetic field lines. Okay, these particles that take 2 to 4 days to come to the Earth. Okay, and what they'll do, of course, is they'll excite nitrogen, oxygen, things like that, and give us those beautiful colors.
And those magnetic field lines around the Earth converge at the north and south magnetic poles. So that's why
right.
you see the auroras in the north and south.
Right.
Because they're closer together, they're more.
No,
Yeah.
because the magnetic field lines, are where these electrons are going. And yes, they're closer together. They're coming down to a point.
More
Yeah.
dense.
That's
Yeah,
in
at the
terms
poles,
of the
Tim,
flux you were talking about.
they're closer together at the poles. Yeah.
Yeah.
Magnetic poles.
I had another question. It's gone now.
Well, I had a question of Tom Whittemore. He just mentioned iron. Is that what you said? Something
Yeah.
about iron?
Well, I was just going to say, when I did solar physics at Lockheed Research Labs, we were interested in imaging the sun, the solar corona. We were particularly interested in the corona at 171 angstroms. And so we had to build basically telescopes that would allow us to see these X-rays. Now, normally when you build a telescope for X-rays, the X-rays will go through anything. And so people often have these shell-like structures for the X-rays to basically bounce off and then finally go to your detectors. What we ended up doing at Lockheed, and that was our special thing, was we coated mirrors, traditional mirrors, like 20-inch telescopes. We'd send them up on sounding rockets. But the coatings we used were usually tungsten, carbon, tungsten, carbon, tungsten, carbon. And so you could image these things directly on, okay, through technically a conventional telescope, but with special coatings. Okay. Because the X-rays would come in and they would basically rattle off of these structures. And there was only about 20 of them, 20 of these structures. And we developed a really neat technique of laying these things down. It was pretty cool.
But I didn't hear you say once the word iron, and yet you said it a lot while ago, talking about the sun. Iron. That's the
Well,
element.
I'm just saying that kind of temperature would ionize iron about 17 times.
Oh, I see.
And there's
no-
iron in the sun's atmosphere, Ron.
That's right.
And the sun's
Because the sun is a
atmosphere
third generation star, so it has iron in there.
Really?
No.
And it does.
It doesn't make it. It doesn't make it. It just got it from somebody else.
Now,
Oh,
when this plasma it's shot out of these coronal holes,
Mhm.
or if it's CME, I've read where there's just tons of this stuff thrown into space. Tons
Yeah.
of plasma.
Oh, yes.
And
Is it?
Tim, look at what Jerry put up here. Remember that yesterday?
Yeah,
Look at that. It's just like we were seeing in our telescopes
yeah.
yesterday.
We had a pretty big filament, Jerry, and it was it looped around.
Yeah.
At first, it was just one big
Right.
looking like a lightning bolt up, but then
Uh-huh.
a little bit later, it kind of looped around.
It was a really neat day, Jerry, for the public to come through and see this stuff. It
Yeah, I
was
have an injured hip and I couldn't
okay.
operate that telescope. Sorry, I
Yeah,
wasn't.
we missed you, but
And
it would have been really
David
great if you were
also,
there.
David moved the little PST to the other side of the telescope, so now I don't get knocked out by the slit anymore. So we could
Oh,
keep the
okay.
public going till about 3:30 or so. And sun's getting really low.
Yeah.
Really
Yeah.
low. God.
well, what are we looking at, Mr. President?
This is all the bad things that could happen when you get one of these, a coronal mass ejection, a CME. This thing is like a loop of plasma following its own magnetic field lines that is eventually going to most likely break off from the sun. And
Mhm.
this unit will come out here like ball lightning or something. And it will come out and head, it takes about 3 days to get to the Earth if it's pointed that way. Luckily, most of them go out the other side or miss us.
Yeah.
Yeah.
And this is what would happen.
Yeah, the one, Jerry, the one that you have there to the left of that loop. Okay, that was our flare candidate yesterday. It was just really amazing. It must have lasted about a half of an hour.
Yeah, I'm sorry I missed it.
God, it was incredible. And Tim noticed it first, and then we got it on the little PST inside the Palmer.
Yeah.
Okay.
You suppose the space guys inside the space station have extra something in their spacesuits to ward off? This is radiation, isn't it?
They're not wearing suits, Ron.
Well, they are
The
outside.
ISS.
When they do an EVA is what I'm talking about.
Yeah.
They have a safe room on the ISS where if
Okay.
there's a CME coming their way, they all squeeze in there with all their friends and they squeeze in it's one cubicle. And it is lined with material that blocks radiation, mostly water. There's a good block up there.
Not lead, which is what I think Superman can't see
There's
through.
some lead there too.
Okay, water.
But
Lead would
water,
work best, but lead is
that's
pretty
amazing.
heavy.
Yeah, lead is very heavy. It's hard you don't want to spend a lot of your money getting that up there.
And
I
stuff with a
didn't
lot
realize
of
they'd use water.
stuff with a lot of neutrons in it works well too. Like I think even Kevlar. So the Kevlar does a dual purpose.
Mhm.
Huh.
Okay, well, this is out of scale as far as what that jet plane is flying in. That's supposed to be the height of the atmosphere.
This is what do they call it? The Casimir line? No, the
Von Karman line.
Von Karman line, yeah. And that's, I think, 60 miles up.
This is not to scale, Ronnie.
No,
I
that's right. It's
understand.
not the scale.
Exactly what I was saying.
So that's Air Force One there, huh?
Yeah.
Yeah, right. Actually, and this is the final topic for today. I thought this was very interesting, even though it was discovered a few years ago. This is our sun, and this is Neptune down here.
Wow.
It's
These are-
really washed out in this
Oh.
display.
Yeah, good stuff, Jerry. Thank you for putting this on today.
Yeah.
Okay.
Well, just out of curiosity, gentlemen, we haven't mentioned this, but has global warming contributed to these new, broader auroras, or is
No.
that just sun action?
What's contributed to it? It's contributed to noctilucent clouds.
Okay.
Huh.
It's not increasing like hurricanes are increasing and fires are increasing.
Noctilucent clouds are.
Mhm.
Noctilucent clouds. I've never heard that term.
Mhm.
Sounds like a
Yes.
future topic.
Yes.
Yeah, high elevation, you seem, glowing.
Yeah.
Oh, okay. And we're looking at what, some parabolic orbits here?
Yes.
Elliptical.
Yeah.
Elliptical orbits, right?
Now this is the sun. This is Neptune.
Okay.
These are trans-Neptunian objects. These are the ones here that are several of them that we've known before. This is the orbit of Sedna. And so all of these particular ones are called Sednides. So this is ammonite, and you see that the blue one, the green one, and the gold one, they're all pointing their long axis away from this in the same direction. That's the pattern that was seen and led people to believe that there was a giant planet 9 out there that's causing these things to line up.
Yeah.
A few years ago, they found ammonite, and they've analyzed its orbit now, and it's going the wrong way. So this is a counter argument to there being a planet 9.
So now it's a planet 8.5.
Yeah.
I was thinking of calling it 8 7/8.
Yeah, good one. That's a good one.
Where is Neptune in there?
That's this little green
little circle
thing around there.
Yeah.
Oh, I see. Okay, it's not named. Got it.
Huge, man. God.
Well, we'll learn.
Yeah, these things take a while.
If I can book Mike Brown from Caltech late in the new year coming up, he'll be talking all about Planet 9. He doesn't zero in on Pluto anymore.
I'll be sure to wear my Pluto shirt that evening.
You do that, Ronnie, and I'm buying you a cake.
Well, I'd settle for you just showing up again like you did with Filipinko.
You got it.
That was fun. Okay, I don't understand this. Where's the sun in all of this?
Right there.
The little yellow
The
guy in the
little
middle.
dot right down the middle.
Right there.
That's the
The
sun, and
tiny-
I thought that was Neptune.
Neptune is the little blue circle around it.
Oh, good Lord. You really reduced the size of the solar system there. Having
Yeah, it's really.
several little astronomical units inside that circle. My
Yeah.
Oh, yeah.
God, a
We
lot.
keep finding our solar system is bigger and bigger and bigger.
So what's the big, huge elliptical? What is that?
That's another object that's
Yeah.
orbiting there with a Hawaiian name.
Yeah, I'm not going to try and pronounce it.
No way.
Oh, that's a hula hula.
You mean it's something we haven't seen?
Kohunua.
They think there's something that's out there on
That's
the ninth planet, but they can't see it, right?
Well, that's what Jerry was just talking about, that this tends to contradict that.
Well, you know, we started 5 minutes late, so we still got 3 minutes to go if you want to make this an hour show.
Yeah, sure.
This is
Sounds good.
Isn't there also a theory that there's another sun, that the sun might be a binary? Have you ever heard that?
That's that Nibiru nonsense.
Is that what it is?
Yeah.
How do you lose another star that's orbiting our sun? You
Yeah,
know?
it's
It's not
internet baloney.
Okay, well, maybe Planet 9. Does anybody remember those dumb movies were made by that guy with heavy on back in the 50s? Planet 9 from outer space.
Yeah, yeah.
With Bela Lugosi.
That's right, it was him.
Is that the one with the gorilla suit with the space helmet on?
Something like that. Okay.
I love old movies.
Um,
The special effects they're special.
Yeah.
Well, gentlemen, I don't know. I keep learning stuff, but I can't hold on to it. It goes away, and I re-ask the question later. But let's meet again because we seem to
You
enjoy
gotta
this.
stick your finger in one ear so it stays inside.
Okay, coming up another week. We're going to have turkey in the meantime. Good luck. Hope you can afford it these days. And doggone, 2 Fridays away from our big December meeting, which is special to our club of both elections and not 1 but 2 in-house science speakers. So, say goodnight, Gracie. I think we're done.
Hasta Nebula.
Hasta Nebula, everybody. Appreciate